Yesterday we continued with hypothesis testing, the ideas of hypothesis testing. Once again, if you want to think of math as a science, okay, and statistics as a science, hypothesis testing is your experiments that you run in science. It is something that, once again, every business, every corporation, every insurance company, anybody deals with numbers, deals with hypothesis testing. And they run tests in regards to gathering data and signifying the probability of something occurring. Most of the time, most businesses now have algorithms, they plug in information and it spews out the information for you. Okay, what hypothesis testing is what the computers will do for you in regards to it. What I've asked to do, or asked you to do for today, was looking at some problems and stating the null and alternate hypothesis. Okay, that was what was for today. We will continue with that worksheet. We'll get into some actual calculations and doing hypothesis testing at that point. So the null and alternate hypothesis that you've developed for that, if you haven't done it, you should be doing it in regards to completing this, because as we go through, you'll utilize that information to be able to solve problems, to do the actual hypothesis testing. Again, it's a statistical test. We had type 1, type 2 error we talked about yesterday. We talked about what would be a type 1 and type 2 error. What you will see in regards to this information, once again, will be a matching section at the beginning of the next quiz. The matching section will be, it will be type 1, type 2 error, what is the hypothesis test, so on and so forth. Go to the back side. We have a level of significance. And when we deal with a level of significance, it is a maximum probability of committing a type 1 error. And once again, all we will be dealing with in this class is type 1 errors. Level of significance is the maximum probability of committing a type 1 error. Probability is symbolized by the value of alpha. And everything that we will do in this class will be dealing with alpha. And that's the probability of committing a type 1 error. Within the problem, you'll be given an alpha value, or you'll be given the term level of significance. And if you look at your t-table, along the top of your t-table, if you look along the top of your t-table, what we've already dealt with is the top line, which was called the confidence interval, which we dealt with last chapter. The next two rows, they have a one-tail and a two-tail test. We'll talk about that here in a few minutes. But then they give you an alpha value. Okay, so you'll have an alpha value. That is the alpha value, the level of significance that we'll be dealing with here. When you get into stats 2, you'll talk about committing a type 2 error, which is a beta value. That is your probability of committing a type 2 error. We won't be dealing with that in stats 1, but it's there. we're going to have critical values. And as we go through this, there's a lot of stuff that we're going through right now. But when we get to actually dealing with doing hypothesis testing, it will look very similar to some of the ideas that we've already talked about. We will be looking at a bell-shaped curve still. We will be still drawing a bell-shaped curve. But what we're going to be now throwing in, rather than throwing in just a z-value and calculate an area, okay, we're going to draw on the bell-shaped curve and we're going to throw in critical values. The critical values separate us from a critical region and non-critical region. These critical values will come from the t-table. Okay, you will get your critical values from the t-table. So as I talked about, as we work through the idea of a t-table, it is if you plan on going to college and you're going to be dealing with some sort of statistics class in college, you're not taking this for College Credit Plus right now, I would suggest that you keep that table, because there are different tables that are out there. This is the one I feel is the easiest for students to comprehend, and also the easiest for you to pull values off of the table. I remember tutoring somebody, it was probably about 10 years ago in statistics. Okay, they needed to take the class to be able to survive and get a college diploma. And the professor gave them one Z table and T table, and I produced a second one for her. She said, "Oh, this one's so much easier to comprehend and understand." So it's one of those things where this T table and the Z tables that we utilize, something that's a little bit easier for you to work with, students able to work with. So do what you want to do. We have a critical region or a rejection region. Once again, this will be all developed and looked at through a bell-shaped curve. It's a range of values of a test value that indicate there's a significant difference and that the null hypothesis should be rejected. It's a range of values of the test value that indicate there's a significant digits and that the null hypothesis should be rejected. So what we have done up till now is we have stated a null and alternate hypothesis. We will run a test value which will look like some of our z-scores that we have calculated. We will look at some critical values, and we will label our bell-shaped curve as a critical region or non-critical region. And what we have the capability of is rejecting the null hypothesis, which, once again, as we talked about, the null hypothesis for the most part are things that are already established and we may not believe is true anymore. So these are values. This is Sir Fig of Isaac Newton's 9.81 meters per second squared. That's established. Okay, that's established. I'm going to put that as a null hypothesis. I'm going to run statistical data, and I'm going to look at, can I reject that hypothesis? Then you have non-critical region. It is the exact same thing. It's the exact same thing here, but what changes is at the very end, the null hypothesis will not be rejected. So it's the exact same thing that we just wrote up above. So range of values, test values that indicate difference was probably due to chance, and that the null hypothesis should not be rejected. Okay, so that's the main difference here, is you're going to have a critical region and a non-critical region. In the critical region, we will reject, if your test value goes into a critical region, we'll reject the null hypothesis. If it goes into a non-critical region, okay, the difference is just due to chance, and that we will not reject the null hypothesis. We have two different types of tests. We're going to have what is called a one-tailed test, and we're going to have a two-tailed test.
Sure.
The one-tailed test indicates the null hypothesis should be rejected when the test value in the critical region is on one side of the mean. Basically, what you're going to run into is the critical region will be just on one side of the mean. That will just give us a one-tailed test. There's two types of one-tailed tests. You can have a right tail and a left tail. What determines which test? Is the ultimate hypothesis. When we're dealing with an ultimate or a one-tailed test, what your ultimate hypothesis is going to be is mu is going to be less than some value, or mu is going to be greater than. We're going to be using the less than and greater than's in there. When it's less than, we're going left. We're going lefty loosey. When we're going greater than, we're going to take a Ralphie. We're going to go to the right. Now, what part of the ultimate hypothesis tells us which way to go here? Look at the arrow. The arrow will tell you, do I go left or do I go right?
Pretty smart.
I'm a keep it simple, stupid person, okay?
Yes. Keep it simple, stupid.
That's me. Okay? And I'm going to keep it simple in my brain. That's how I keep it simple in my brain. So we look at the null ultimate hypothesis tells us, do we have a left tail or right tail test? When we have a two-tailed test, the null hypothesis should be rejected. Once again, we're looking at rejected when the test value is on either side of the critical region. So these are two-tailed tests. When we look at a two-tailed test, two-tailed test is when your null and ultimate hypothesis are equal to and not equal to. That will give us a two-tailed test. Okay, if we go back to our notes from yesterday. On the backside, we stated the null and nullable hypothesis. Okay, so we're going to go back to the notes from yesterday, where we stated the null and nullable hypothesis. We had 6 different scenarios. We didn't do one of the problems because I didn't throw a number in there. Starts out with the researcher thinks that expected mothers use vitamin pills, the birth weight of babies will increase. The average birth weight is 8.6 pounds. So we look at the null and nullable hypothesis in the first one. Would this be a left or one tail or two tail test? One or two tail? One tail test. Would it go left or right? Okay. What does they hope will be true? We look at the alternate hypothesis. Which direction is the arrow pointing? Right. So it will be a one-tail test going to the right. Okay, what you should be doing each and every time on a problem, as you go through the problem, to keep it simple in your mind. Okay, to keep it simple in your mind, because once again, I throw a lot of stuff at you. You've never seen anything like this before. Okay, when you can write stuff down, that takes it out of the clutter of your brain. Because your brain has a lot of stuff down here, but if you write it down, it takes it out of whatever the clutter is in your brain. So once again, we just take a look at the alternate hypothesis. What do we look at here? Alternate hypothesis is mu is greater than. So this is a one tail right. Okay, because we're talking about less than or greater than, so it throws us into one tail. We have arrow pointing to the right. Go ahead and go through the rest of your problems. Go through the rest of them. Say if they're one tail or two tail. Write down one tail or two tail. If it's one tail, is it one tail right or one tail left? Okay, you're looking at the notes from 2 days ago. We had all these scenarios that we threw at. Okay, write down one tail, two tail. And if it's one tail, throw down left or right. Check your answer with somebody around you. Once again, when you're dealing with less than greater than, that's your one tails. Alternate hypothesis tells you go left or right. When you have equal to, not equal to, that gives you two tail. They probably have it in subsequent emails that I don't read much. So if you say, I'm trusting your ability to be able to tell me a truthful thing, and your integrity that you're going to tell me a truthful thing, and that's fine. Second one, what do we have in the second one here? Matthew, since you're leaving, what do we have? One tail, two tail?
For the very second one?
Yeah.
One tail.
Which direction?
Left.
Left. Third one down, See, mean score, we have raise alert, not sure which one. Hannah, which one do we have here? One or two tail? Okay, it's two tail. Then do the next one. Let's see. Chemist additive inventor or invents an additive. Jason, what do we have with this one? One tail or two tail? Hannah, what do we have? One tail, left or right? Okay. Contractor wishes to lower the bills. One tail or two tail, what do we have? Madigan, what do we have? One tail, which direction? This, once you write the null and alternate hypothesis, what you should then write is one tail or two tail, left or right. Okay? One tail, left or right, or two tail. You should write that there because, once again, you're going to be getting critical values. Critical values are going to be coming from our t-table. If we look at the top of the t-table, okay, we did confidence interval, then line 2 of the t-table, it says one tail and an alpha value. Okay, so that will tell us the critical values, or we have a two tail and the critical value or the alpha value. Okay, so you need to know is it one tail or two tail and what the alpha value is. So if you can write this down, it makes it a little bit easier. Once again, it takes it out of your brain a little bit more. Makes it a little bit easier for you. And we're going to start going into some calculations now. How do we deal with calculations? How do we do the actual experiment, the mathematical experiment? Now, if we look at our t-table, okay, our next step is going to find critical values. Okay, what I have here is critical values here. Okay, I have critical values here that are listed. But these are Z critical values. Okay, these are Z critical values. If we look at our t-test, our t-table, if we look at our t-table, let's go a one tail test and an alpha value of 0.10. So along the t-table, let's go to the one tail row over to the alpha value of 0.10. Okay? So we go one tail, alpha value of 0.10. And let's drop that all the way down to the bottom. What you'll get is the 2.82 or 1.28. Okay? If we look at a two tail and an alpha value of 0.10. So we look at a two tail, so let's go to the two tail column or row, and let's go down go over to the alpha value of 0.10. And drop that all the way down the bottom. We get our 1.645. So our critical values we can get off of our table here, once again, just looking at the alpha value, and is it a one tail or two tail? So it's important to know those two things. If a z-score falls into a critical region, this is a test score. If your z-test score falls into a critical region, you will reject the null hypothesis. if the Z-test score falls into a non-critical region, you fail to reject the null hypothesis. So you're going to do a test value. Does it fall into a critical region or a non-critical region? If it falls into a critical region, you will reject the null hypothesis. You'll get rid of the null hypothesis. Sir Fig of Isaac Newton was wrong. You reject his 9.81 meters per second squared. If you fall into a non-critical region, you fail to reject the null hypothesis. You still may not accept it. In your heart, in your brain, in your eyes, you still may not accept it. But statistically and mathematically, you don't have any evidence to say it's wrong. Okay? So you just fail to reject the null hypothesis. So two scenarios when it comes down to, you will either reject or fail to reject the null hypothesis. When we were dealing with confidence intervals, we did a final statement. We were 95% confident the population mean for some sort of thing is between this value and this value. Well, what our final statement is going to be now is the evaluation of, we have enough evidence to reject the null hypothesis of the population mean being this value. Or we fail to reject this null hypothesis of the population mean being a specific value. So we will either, that will be your final statement, rather than I'm 95% confident something's happening. You're going to write a statement, I can reject the null hypothesis, blah, 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 or I fail to reject the null hypothesis. Once again, the null hypothesis still may be false. Once again, it still may be false, but there's insufficient evidence to reject it. Okay? Once again, type 1 error. OJ. That's type 2, my bad. You fail to reject the null hypothesis when it is actually false, and you should reject it. Well, what we have here is a test value. Statistically, we have to calculate a test value. How we calculate this test value looks just like our central limit theorem Z value. If you remember back to our central limit theorem, it was the mean minus the population mean divided by the standard deviation divided by square root of n. That was our central limit theorem. This is the exact same way we deal with our test value. So if we do a one-tail, so let's look at one-tail right. We have a bell-shaped curve we've been dealing with because we're talking about normal distribution here. Let's go down here. We want to go through our steps. We state the null and alternate hypothesis. We'll get back up to that. We'll state the null and alternate hypothesis. You may want to also state, is it one tail or a two tail? You don't really have to identify the claim. I'm not going to be too huge on the claim here. But write the null and alternate hypothesis. state, is it a one tail or two tails? Of a one tail, is it left or right? The second thing we find is we find our critical values. We get them from the T-table. So if we look at a one-tail test, right. This right tells us where we're going to throw in our critical value. This is where we're going to throw in our critical value. We have a non-critical region. And a critical region. Once again, that critical value will separate us into non-critical and critical. The non-critical region is going to be the bigger of the regions. The critical region will be, once again, if we take a look at this, why we call it a tail test to the right is it tails off here to the right. So my bell-shaped curve tails off to the right, so I have a tail over here. I have a tail over here, and it's on the right side of the mean. Here's our right side of our mean here. Okay, so we have one tail, we have non-critical, we have critical region. If we look at a two-tail, we have our bell-shaped curve again. But now we need two of these tails. Okay, here we just had one of the tail here. It tails off. If I'm dealing with the one tail left, it's going to be on this side. But here I have two tails. Here's our critical values. I'm on both sides of my mean here. We have a non-critical and critical regions. All of your problems will set up and look like one of these two things. Or if you have a left tail test, it's just going to go on the other side of the bell-shaped curve. So we find our critical values from our T-table. We compute a test value. We compute our test value, which is x bar minus mu divided by standard deviation divided by square root of n. We make a decision whether to reject or fail to reject the null, or reject the null hypothesis or fail to reject. We may want to place our test value on the curve, whatever this test value is. My test value may fall into here. Or my test value may fall over here. If my test value falls in the critical region, I reject the null hypothesis. My test value here falls in the non-critical region, I fail to reject the null hypothesis. If my Z test value falls in here, non-critical region, fail to reject. It falls over here, I fall into a critical region, we reject the null hypothesis. So you look at where your test value falls on the number line. What side of the critical value do you have? Then you make a decision, do we reject or we fail to reject the null hypothesis? And the last step is to state your, summarize your results, or state your conclusions. And your conclusions are going to be, I reject the null hypothesis of the population mean being this. Or I fail to reject the null hypothesis of the population mean being less than the specific value, or equal to a specific value. We will stop there today. We won't do anything else. We will wait till Monday and we'll go to the backside and we'll start doing some problems on the backside. When we have the three amigos back there are back in the class and Matthew over there are back in the class. And Matthew's here on Monday.
If he shows up.
And we got Corey. I know it's the senior day after prom. And I understand that typically they start getting a little off and they might not feel the best. That's just typical. So we'll deal with the problems on the backside on Monday. Alright, QED is done.